Thank you very much. Thank you for this very kind introduction, also for basically describing half of my talk. So what do I do now? You know, okay. Let's go to slide 12. Well, very good. It's an absolute pleasure to be here. I must say it's my first time in Singapore, and it has been a delightful time. So let's end the week in a good way. So what I'm going to do in this talk is try to give you, in some sense, a panorama through example. I'm going to discuss percolation theory, tell you a little bit what this is, tell you one or two things that we know about it, one or two things that we don't know about it, just to see that there are many things for you to do if you want. But through this story, in some sense, it's a bigger story that I will tell. It's the story of statistical mechanics, how you study matter, and in particular phase transition, change of behavior in materials. So that's what I will do, but again, through this specific example of percolation. And I'm going to even do something more restrictive. I'm going to start with an example of percolation, so an example of example. And I'm going to start with a game. I don't know if you know this game. It's called the Hautes game. I recommend. The rules are extremely simple. You can explain them to really a 6-year-old. It's much simpler than chess, for instance. But the actual strategy to try to play well at this game are very delicate. So the game is the following. You have a board, let's say 5 by 5. It could be 10 by 10, 11 by 11. And you have two players, say Anaëlle. She plays in blue, and Bastien plays in yellow. I realize that these are very French names. But you know, we learn many things through math. So what is going to happen is that Anaëlle is going to color hexagons in blue, Bastien in yellow or orange, okay? And they do it each other, one after each other, okay? And the goal for Anaëlle is to create a blue path from top to bottom. The goal for Bastien is to create a yellow path from left to right. Okay, so let's just play or act like we play. So they play, you see, they color each one after the other. There is no reason you should color next to what you already did, which, by the way, is very funny because if you make anybody play this game, I already told you something useful. People will almost always, play contiguous cases. And this is a very, very bad tactic. So it's very funny, like the intuition is completely wrong from step 0. So you play like that, and let's say, you arrive, for instance, at this stage, and there what happens is that Bastien won, right? He created a path. It doesn't have to be a directed path. You can do whatever you want, but it's a connected path from left to right. So first question for you, who thinks that there is always a winner in this game? You are alone. Who thinks that there is not always a winner in this game, that you can do a draw? I'm inferring that everybody else didn't understand that you should answer yes or no to this question. What was your plan? So anyway, okay, so one person said yes, 5 said no, and the rest of you didn't understand the question. Very good. But still, I like it still because majority of the people who answer was wrong. There is always a winner at this game. I'm going to explain to you why in a second, but just for those who get immediately bored or really don't like what I will tell you next, you can think, is there a winning strategy, meaning a perfect way of playing for one of the two players in such a way that what the other one plays, even if the other one tries to play as best as possible, it will always be you who wins. Okay? So, okay, there is always a winner, and in fact, it's fairly easy to see for the following reason. So you cannot have an equality because if you would have an equality, you agree that this would be because you color yellow, blue, yellow, blue, yellow, blue, and you arrive at the very end. You colored all the cases, but all the hexagons, but there is no path of blue from top to bottom and no path of yellow from left to right. So let's assume that there is no path of blue from top to bottom. And what I'm going to do is just, a change of vision about the problem, but it's a very simple one. I'm going to color in light blue all the hexagons that are the blue hexagons that are not connected to the bottom. And when you do that, there is something that appears immediately normally, is that if you look at the dark blue hexagons, of course, no dark blue hexagon is here, because otherwise that would be a blue path. That would mean that there is a blue path from top to bottom. But that means that if none is there, then just above those guys, those blue hexagons, there is a yellow path from left to right. So if blue didn't win, if Anaël did not win, then Bastien won. Okay? Very good. So now we have 95% of the audience who is like, oh, why didn't I answer, right? Remember that next time I ask a question. Okay, so now imagine that you are alone at home, you are a little bit bored, internet is down, you know, these things happen sometimes, at least in France. And so what do you do? Imagine you have a board game, and you are alone, so you cannot play with somebody. So what you can try to do is to play alone. It's not going to be a super fun game, but you can do the following. You choose an hexagon, and you choose the color of the hexagon independently at random. So what you do is you take a random coin, for instance, a Fields medal, and you toss it. This is just that you see how it looks. So this is Archimedes, and so you toss the coin. If you see Archimedes, then you color it in yellow, otherwise you color it in blue, and you do that for every hexagon, okay? By the way, the order in which you choose the hexagon is completely irrelevant. It's not going to be important. There is no tactic here. It's not a game, in fact. It's a game because you throw the coin, but that's all. So you color everything, and then you ask the question, is it blue or yellow that wins, right? So here, for instance, it's blue. And you agree that who wins, blue or yellow, will depend on the toss coins, right? The coin tosses, sorry. So what here I would like to ask you as a question is, what's the probability that blue wins? Okay, does somebody has an idea out of the 95% of the people who didn't answer the first question? What's the probability that blue wins? Don't be shy. Half, okay, very good. So that's indeed the probability, but why? That's the next question. To your opinion, why is it that there is 50% chance that blue wins here and 50% chance that yellow wins? You can raise your hand, you can... Don't be shy. You know, I like to give this part of the talk I already gave to middle school students. And there, you have to fight, because everybody wants to answer. People start running at you, running at each other. I mean, it's... so, yeah, you want to answer?
Yeah, because if I color the yellow blue, I color the blue yellow.
Yeah, that's not what I heard the first time I gave that to a middle school student. Yeah, so this is indeed, I think, for once, and this is surprising, but for once, it was basically the full answer right away. It's very funny as a question because people have the intuition of 50%, but usually for a wrong reason. So what you hear usually is, well, the coin toss is 50-50. Or you hear, or maybe combined, you know, there is a winner. It's either blue or yellow. Well, either blue or yellow tells you that the sum of probability of winning for blue and yellow is 1, right? But it doesn't tell you that it should be the same. The 50-50% coin toss is not also sufficient, because imagine that your board will be made just of one column like that. Then clearly for the blue to win, all hexagons should be blue. For the yellow to win, one of the hexagons should be yellow. It's much simpler for yellow to win, and the probability will not be 50-50. But what you said in addition was indeed true, is that what you get here, if you put your head like that, right, and you imagine that you are color blind, or I mean, that you change blue and yellow, then what you realize is that yellow is exactly playing the same game as blue. So if winning probability of one is equal to winning probability of the other one, and the sum is 100%, it gives you 50%. So, I mean, of course, you didn't have to do that. I could also do it, but I like to see people doing that. Yeah, 50% winning. So this random coloring of the hexagons, it's a model of percolation theory. It's really one example of a percolation model. And I want to tell you a little bit about the scientific interest of this model. So first, the name. The name comes simply from making coffee. You know, mathematicians like coffee. They invented this model. So first thing they thought, like, what is a porous behavior? And coffee. So what you do is, right, so for the young people, this is a coffee machine. You don't just press on a button having, you know, very nice gray hair and looking like Clooney. No, this you can also heat here, and the water is going to boil and go through the grain of coffee. And here you can imagine that just the hexagons represent the possible positions, and if it's in brown, that means there is a grain of coffee. If not, then water can flow through. And what happens is that if Bastien wins, if you have a brown here, but I mean a yellow path from left to right, then water will not percolate through it, and you will not get a coffee, which is sad. Okay? And on the other hand, if blue wins, maybe blue wins, but not too easily, like there is a few paths from top to bottom that meander quite a lot, then you will get a nice coffee on the other. Okay? So that was the original motivation, but obviously you can imagine that if it was just making coffee, the theory would not have been taking roots in the middle 20th century. I mean, I think probably Italians know how to do that for thousands of years. So, I mean, there are many percolation porosity phenomena. For instance, you can look at coal and try to see whether molecules of gas go through coal. And that's actually one of the early experiments about percolation. Rosalind Franklin, from the DNA story, she actually studied during Second World War the coal and how much temperature and size of molecules impact whether the gas is going through the coal. In fact, it was not to try to see whether you can make a good mask or something like that. It was to try to measure the density of the coal. So that's another example. Let me give you an exotic application. It's one that I like very much, even though I truly hope that the person will never ask me to go there. So Kenneth Golden actually used percolation to study melting of polar ice caps. So he actually goes to Antarctica. And the phenomenon there is the following. When the sun is hitting the surface of the ice, a thin part of the ice melts, okay? And the water is going to percolate through the holes in the ice, okay? And so then when water goes down, I was told to stop saying when the night is coming, because you can wait for a long time in Antarctica. So it's a 10-year-old that told me, but I don't understand. It takes half a year to get to, I mean, yes, okay, well done. So when water goes down, when temperature goes down, the water may freeze again. And what do we know about frozen water? It takes more space. So if the water percolated through the ice, took all the space, and then turned into ice, then it's going to break the ice even more, create an even more broken part of the ice, and then accelerate the melting later on. Right? So there is an acceleration of ice melting due to a percolation phenomenon. So he's studying exactly how this is done and what are the parameters of the percolation model, how you can predict how it's going to melt, etc., etc. Okay, that was for the non-mathematical interest. There are many others. It was said that you can model also spread of a disease or rumor thanks to percolation, etc., etc. I mean, I could do a very long list of applications, but let me now focus on why we are interested mathematically about this model. And the main reason is that this model exhibits what we call emergent properties. And this is something that goes way beyond this talk. An emergent property is a property that is not apparent in your system a priori, but that emerges when you look at it the right way, maybe when you tune the parameters in the right way, etc. And here, just this is a nice picture. For instance, typically what you will start seeing when you look at percolation models, it's random fractals. I will come back to this later. Things that has no reason a priori to exist in the system at the beginning, but that emerge from the complexity, if you want, of the model that you are considering. And these kind of properties are really the properties that we are interested in. Because if you think about the porosity phenomenon, I think none of you thinks that, please do not think that when you look at your coffee machine, the grains are made of hexagons on a planar surface, and that, right, I mean, this is clearly a model. It's a caricature, a mathematical caricature of what happens, but it's not reality. Reality is much more complex. So you may naturally tell me, but why do you oversimplify real life that much? We do it because there is a beautiful phenomenon, a gift of nature, if you want, that was noticed first by Leo Kadanoff, a physicist. And I'm going to just actually quote his words because I find them very enlightening. He's saying the strategy consisting in studying a physical question using a largely simplified model, we are clearly in this context here, is justified by a property of physical systems called universality. So what universality means is that the behavior, basically, of your system doesn't really depend on the very delicate definition that you made. I consider the hexagons, I could have put square. I consider that really the color of the different hexagons are completely independent, right? I mean, if I color an hexagon in blue and I take another hexagon, I'm tossing a new coin. So there is no information that is going from the color of this hexagon to the color of this hexagon. This perfect independence, I could twist it a little bit. I can do many twists around my model. It will have the same behavior. And that is this universality property, and that's exactly what we are seeking when we do statistical mechanics, because if you have such a property, then there is clearly something you want to be doing, and that's what is explained in the last sentence. In order to study such properties of your models, if they are always the same, then it makes sense to study the simplest possible model. Just take the model that will be the simplest to study. It will have certain properties. Because it's a simpler model to study, I may have chances of deriving these properties mathematically, but then these properties, they should be the same in all the other systems. Okay? So that's the reason why we are so interested in this model, is that what we are doing has a universal impact in some sense. So let me give you a few examples of universal property, just that. And the first one is actually a very cool one. So we said that the winning probability for our game, the winning probability is 50% when we randomize, right? If I ask you the same question on this board, a rectangular board, then the whole argument collapses. I'm so sorry. You were the only one daring to answer, and I'm breaking your toy. So there, you cannot do the symmetry simply because now it's wider than tall, right? You can take any shape, in fact. So in France, this one works very, very well. I don't know who recognizes this one. It's Mbappé, right? So it's one of our national heroes. So the kids start, screaming, Mbappé. Well, except in Marseille. But in Paris, it works well. So you take any shape you want. You divide in 4 sides. And you put hexagons inside. And you want that there is a path from blue to blue for the blue. And you try to look at the probability of this. And again, because you don't have symmetry anymore, You don't know what's the probability of winning. But you don't know, but you can still ask the question. And this question was asked, not for this model, but for a slightly related model, in 1894 by Devolson Wood. Can we compute the probability of winning? It was actually in this context explicitly. And the editor at the time, so it was in Journal of American Mathematical Monthly, the editor has this editorial answer, oh, very good question, give me an answer by next month, and I will publish it. The poor man was wrong by 107 years. Too bad. Try again. I think he paid for all the editors that tell you that writing is easy and will not take you time. So 107 years, and in fact, the person who answers this question got the Fields Medal. So there is a rule when you give math talks. It's an unspoken rule, but it's a rule. You should never show a formula because people panic, start to... So I'm going to do it nonetheless. Yeah, that's don't learn from your mistakes. No, you should learn from your mistakes. So this is the answer. Actually, it's complicated even to read. I don't want you to understand, but I just wanted to show this picture because for people who are not yet like mathematicians, professional mathematicians, this may look scary, but it looks scary because we are not telling something as mathematicians to the rest of the population, is that a formula is before everything just a way of telling a story. And the story behind this formula is actually quite cool, and I want to, well, I should not have said that because if you don't find it cool, I will feel very much alone, but it's quite cool and I want to tell you about it. So in order to tell you what this formula tells me, so I don't even know how to read this formula. I always forget what eta of h, what's the mathematical name for it. It's not important. I know the story behind the formula, and I want to tell you this. So the story behind this formula, in order to tell it to you, I need to tell you about a certain way of what we call a certain way of deforming objects. So if you take a ball, and let's say you throw it, like you shoot in it, the ball will go very far away, but any angle on the ball will be preserved by this transformation. So this transformation is what we call a conformal transformation. It preserves the angles. If I just pump air in this ball, it's going to blow, it's going to grow, but the angles are preserved. Okay? Same thing, if you rotate, you translate, or you increase the size, it's the same. Do you know another conformal transformation? Do you have examples of conformal transformation? So just a way of modifying something in such a way that the angles are preserved. I have a hint, you know at least one other. Yes? So reflection is a very good example because it shows that I'm doing a very poor job. So it was oriented angle. So indeed, if I don't look at the orientation, you are perfectly right that a reflection is also a conformal map. But in fact, you need to preserve the angle. But this is, no, don't do this face. It was a very good answer. It was an excellent answer. It's my part of the responsibility to jump on it, but this is very good. Reflection was indeed one thing I was expecting. Maybe now it's going to be a little bit more clear or less clear, I don't know. Right? I mean, when you take the Earth and you remove the polar, the two poles, you are actually used to see this in a very different way. You are used to see it on a page. It's a Mercator projection that is going from this ball into your page, into your planisphere. I actually not quite sure how you say it in English, but that's a proof that that's the first time I give this talk. But you see, the important thing is that here, if you look at latitudes and longitudes, I mean, they are intersecting orthogonally, and this is still the case here, fortunately for every navigator, right? Oh, this speaks here, right? So if it was not a conformal map, this will make the life of people using these maps extremely difficult if the angles are not preserved. So this is another example of a conformal map. And in fact, you have to trust me, but there are many, many, many conformal maps. an enormous number of conformal maps. So now what's the connection between this story about conformal maps and this horrible formula? Well, the connection is that this horrible formula is exactly saying the following. It's saying if I take two shapes, two boards, okay? If I can transform one board into the other one by a conformal map, then the probabilities are the same. The winning probabilities are the same. A priori, right, it seems completely crazy that there will be such a symmetry in my system, and yet that's what happens. So it's only in a limit, you see here there was a limit, it's only when the hexagons get smaller and smaller. So you take a bigger board with a certain shape, but indeed there is this emergent symmetry in the limit. This new property that is not true at all. For instance, I said that a rotation is a conformal map. Take your board like that. Now take the same shape, rotate it, but still do the hexagon horizontally. It's not clear at all why you would preserve the winning probability. And yet that's what happened. That's what this formula says. So beyond these funny symbols, the true story behind it is same winning probability for boards that are conformal images of each other. Okay? And the person who solved that got the Fields Medal, and he was my PhD advisor. That was not me. Well tried. Okay, very good. Second emergent property, just because this one is probably even cooler. So as I said, there are fractals that come out of the study of these models. So what is a fractal, right? I mean, if you take these different shapes, for instance, what you can try to do is to cover them by squares of a certain size. So if I take squares of size epsilon, how many squares do I need to cover a segment of length 1? I would need roughly 1 over epsilon such squares. And if epsilon tends to 0, the fact that it behaves like 1 over epsilon to the power 1, tells you that this is a one-dimensional object. The dimension of this is 1. If you do the same on a square, how many squares of size epsilon do you need to cover a square of size 1? You need 1 over epsilon squared. And this squared is why the dimension here is 2. If you would go to a cube, it would be 3, etc. These are the dimensions that you are used to have, used to work with. These are the standard dimensions. But there is no reason you should restrict your attention to objects that have these integer dimensions. For instance, you can look at this shape. It's called the Van Gogh snowflake. And when you go to smaller and smaller squares, in fact, there, you will need epsilon to the log 4 over log 3 squares to cover the boundary of this snowflake. So the dimension, in the same way that the dimension here is 1 and the dimension here is 2, the dimension here of this object should be log 4 over log 3, a non-integer dimension. And that is basically what we call in physics fractals. You probably heard about fractals as scale-invariant objects. I like sometimes to rephrase this as object with dimension, which is non-integer. Okay, what's the connection? So this is an illustration of what you would do with Brittany. So it's a far west side of France. I'm zooming in every single time, and I get basically the same fractal shape. And the dimension, the dimension of the boundary of, I mean, of course, don't tell that to somebody living in Brittany, but the boundary, the dimension of their space is non-1, non-2, it's something in between. So what's the connection with percolation is that in percolation, if I look at the boundaries between blue and yellow, and I was supposed to have a beautiful picture here, which disappeared, my fault. So there was a beautiful big picture of, you have to imagine, close your eyes, listen to my delightful voice. Imagine a huge board of yellow and blue a boundary between shape blue and shape yellow. And what I'm saying is that, oh, it did appear. What happened? What did I do? My imagination is much stronger than I thought. Okay, you also see that, right? It's not just here. Okay, sorry for that. So yeah, here, beautiful. So you see the boundary, where the boundary in this case has a dimension 4/3. And the 4/3 is the same dimension that you see in natural erosion phenomena, in particular on Britannic coast. So the universality here, you see it because I'm taking different models. This is another percolation model. And again, the boundary has dimension 4/3. So the same dimension for different objects, universality. Okay? So we want to understand that. I have no clue when I started. Absolutely no clue. So when did I start and how much time do you still have? Otherwise, I keep going until the end, right? But until Leslie starts, 15 more minutes. Okay, very good, very good. I mean, very good for me. For you, it's maybe a little bit less clear. Okay, so part 4, because you expect universality, then it seems very natural to try to explore the different models that you could cook up. So for instance, in fact, most of the time, the way we look at percolation is to look at random graph. So a graph, right, is a collection of sites connected by edges between these sites. This is a big graph. And for instance, one thing you can do is you can choose a very regular lattice, for instance, the square lattice, so just, the paving that you will get by squares. And you could decide that you are going to pick a random subgraph of this graph, exactly like we were randomly coloring the faces of in the hexagons in the previous model. Here you could choose to randomly color the edges of the graph. You would say for each edge, I color it in red with probability p and in gray with probability 1 minus p. And then I look at the set of red edges. This is probably the most famous percolation model and the simplest one. So it's very similar as before. Before it was tossing a coin at 1/2, 1/2. Here is just a biased coin. It's red with probability p, doesn't have to be 0.5, and gray with probability 1 minus p. And just to tell you immediately how rich the system is, these are 2 simulations. So here what I did is that I colored the connected components of your graph, meaning the places, so two points are colored in the same way here if there is a red path between the 2. Okay? And here, the simulation is for 0.499, very close to 0.5, but slightly below. And what you see is that the connected components are very small. Another way of thinking of the connected components is that if I pump water in this red area, it will go exactly, if it's allowed to go through the red edges, it will go exactly to all the red edges and nothing more. So you see that the water here will not flow anywhere, basically. It will stay almost where I pump the water. So this will be a typical example of a medium which is not porous, right? It will not let water flow. This is the same simulation at 0.501. Just 0.002 more. And there it's not a problem of simulation. The huge red area is a connected component. If I pump water here, I get water here. So there is you see that the dependency in the value of P is extremely, extremely, extremely strong. That's usually a very good sign. It means that something very complex is happening. So that's Bernoulli percolation. Forget about that. Now, let me construct another percolation model for you. It's a model that is made out of a magnet. Okay? You think of a magnet as a collection of many, many, many tiny constituents. These tiny constituents, you think of them as small magnets. Okay? I didn't make this beautiful animation. It took me a lot of time to explain to the person what I wanted to have, but I like it very much. So you see, you zoom in, it's like your magnet was made of tons of tiny magnets. And what you can do is ask that they are regularly spaced. You put them in the middle of the faces of your square lattice, for instance. When you do that, then what you can simply do is you can imagine that the magnets are either pointing in one direction or the other one, either north or south. It's a big simplification, but why not? And then you can color, this is my north and this is my south. We are mathematicians, so we don't care so much about reality. Maybe I should have put it like that. But so if magnet is pointing that way, I color the face in blue. If it's pointing that way, I color it in red. Okay? And I do a very big simulation. I obtain some random coloring again, in fact. And I can make an analogy with a very large board coloring. And here you see that you can ask the same kind of question. So of course here it's blue or red squares. Here it's blue or yellow hexagons. But I can try to make the analogy between the two. And I see that maybe the shape of the large blue clusters here has something to do with the shape of the large blue clusters here, for instance, blue areas. You can study the two models in the same way. This is another example of a percolation model. Percolation, again, porosity, but this time, I cooked it up from magnetism. Like I took a magnet and I cooked up a percolation model out of it. So there is no reason you should bound your imagination to considering percolation model only for porosity. You can do it for other models. And in fact, that's exactly why, in some sense, math sometimes has some predictive behavior, predictive ability, is because by going to a next level of abstraction, you may see that different phenomena, in fact, share common features. And here it's exactly what happens. Okay. So this is a gallery of monsters, different models that you can cook up. You see, this is a model for the spread of a disease. The more blue you are, the longer you survived. That's not optimism, but this is a model of, again, so here you can look at the connectivities. Here it's black and white. You can look at the connectivity as well. This model comes from random waves. And in particular, it's related to localization of electrons in material. Nothing to do with porosity. But you can look at this percolation model. This is a percolation of balls. I mean, you can do a 3-color percolation. There is no problem with it, etc., etc. You have a wide zoo of models that you can study, and they will give you very interesting behaviors. So what's the connection with my research? And like that, I will finish the talk. What I do is that I actually like to study phase transition, so brutal change of behavior in a system. How can you see percolation as a phase transition? So let me now do the following. I'm going to, again, take the hexagon because the hexagon, in some sense, it's more visual. But what I'm going to do here is that I'm going to increase the probability that the hexagon is yellow. So you see new yellow hexagons popping up. Okay? Is it clear what is happening? I'm increasing the probability that that each hexagon is yellow. And the dark yellow are the yellow hexagons connected to the left. Okay? Did everybody understand the simulation? Well, I think even if somebody would have said no, I would have kept going. I have to be honest. So let's make a bigger picture. Now the dots here are tiny hexagons. And here you see that some hexagons are deeper yellow. They are those that are connected to the left. And what I want you to understand here, or to feel here, is how much things do not change for a very long time. And then fairly brutally, here I think we are at 0.49. And here very brutally you see you have new areas, boom. All of that, you see, very quickly you get from something that is not porous at all, in the sense that the yellow edges on the left are those that would get water if you would pump water on the left. It almost doesn't go anywhere. And then very brutally it gets to something where it's percolating everywhere. And if you just remember the flash of these new shapes, they were very rough. There was, it was not that they are creating a straight path. There was this fractal structure at what we call the phase transition. Brutal change of behavior, and at the phase transition, there is these emergent properties. Okay, so in fact, here you saw that when you vary P, you go from a phase where you almost don't percolate to a phase where you percolate. In fact, what you could do is, in an infinite system, you could look at the probability that there is an infinite connected component. That in some sense, if you pump water at 0, what is the probability that it goes up to infinity? Okay? So let's call theta of P this probability. And what the simulation before suggests is that this probability is 0 for a very long time. It's impossible, basically, to go to infinity. And then at a certain point, that we call the critical point, it starts to be strictly positive. And one thing that physicists love to do, and if physicists love to do that, we also do, that's my love, for physicists, that I'm exhibiting in front of too many people. But so what happens is that as soon as you are above the critical point, it's going to be strictly positive, but you can look at how it behaves when P is very close to PC. And there is something very interesting that happens, is that the probability that 0 is connected to infinity behaves like P minus PC, so it's kind of the distance to the critical point, to a power, beta. So question, from your point of view, what is the value of beta? Do you have a clue? Hint, this was the moment where it's good not to answer. It was not earlier. So beta, so let me tell you, beta in dimension 7 and more, it's 1. So it's like P minus PC, so it will be a nice line like that. In dimension 2, like everybody would have guessed, it's 5/36. How a model can make 5/36 emerge, right? I mean, the first time I saw that, I was like, this is cool. I really want to do this as a researcher. And nowadays, I still don't really know why it's 5/36. But so yeah, you get this amazing exponents, 5/36. And you get it when you color in blue and yellow the hexagons. But you also get it if you color in red and gray the edges. You get 5/36 again. Exactly the same exponent. It's called a critical exponent, and it's universal, and it's a beautiful question to try to compute these things. By the way, in dimensions 3, 4, and 5, we don't know even what this is equal to. We have numerical approximations, but we don't know what this is equal to. And I will finish with a question for you, is that there is a natural question when you look at a phase transition, is to decide whether it's a continuous phase transition or a discontinuous phase transition. Typical example of discontinuous phase transition, water to ice. The pressure or the volume that water is taking just increased by a factor 10 or 20%, I never remember. When it gets into ice, that's what I mentioned a little bit earlier. There is a discontinuity in the phase transition. If you take, for instance, magnetism, so if you take a magnet and you heat it, there is a phase transition. There is a point where the magnet stops to be a magnet. And if you look at the strength of the magnet, it's going to decrease continuously to reach exactly 0 at the critical point. So it's a continuous phase transition. You can ask the same for percolation. Is the probability that 0 is connected to infinity continuous? I told you that it should, in fact, be continuous just before. I told you that it should even behave like P minus PC to a power. But just one thing, in dimension 3, so if you take a 3-dimensional model, you take like hypercubic lattice, every edge is open with probability P, closed with probability 1 minus P. We don't know how to prove that it's continuous. It's the biggest open question in our field, and you see it's fairly simple to state. So for the young and courageous people in the room, you can try a little bit to do percolation when going back home and try to solve this problem. Thank you very much for your attention.
Thank you, Prof. Please remain on stage for the Q&A. And now I would like to invite Professor Juan Pablo Ortega Associate Chair at the School of Physical and Mathematical Sciences, on stage to be the moderator for the Q&A session.
Hello, good morning, everyone. So I wanted to start by thanking you for the talk. It was fantastic. And also, it was not said before, but before coming here, we had this session with the students. We had this wonderful breakfast, so it was with Professor Valiant. So I wanted to thank you on behalf of the students, because it was delightful, and I'm sure that some of the things that you said will have a lasting effect in their way of thinking, and for sure in their career.
Positive one? Or?
I'm sure. So let me break the ice and start with a question for the mathematician, because my dear colleagues here in the audience, they know this very well, including Professor Ling Sang, who happens to be a mathematician too. So mathematicians will play a role in the scientific landscape of, how would you call it, of a free electron, or a cultural exception, as we would call it in French. But because, we are not so much into impact factors, multi-million grants, the way in which our research is assessed is different. And you happen to come from a very interesting institution, the IHES, which is extremely successful in producing mathematicians with a very high level, and who eventually get a lot of Fields medals. So my question for you was, in your opinion, what is the work ethics? What are the working conditions that mathematicians need to flourish, to blossom, to be productive?
I think we are very lucky in mathematics that the competition takes much less importance than in other fields. In some sense, there is clearly no advantage in competing in mathematics. This is due to several things. The first one is that it's true that we cost less, as many of the people in our universities remind us when they want politely to tell us that they will not give us money. But so we cost less, we need less, so in some sense we also compete less with the next person in line, and it becomes much more interesting to share ideas instead of trying to conceal them. Also maybe because we are slightly farther from the direct industrial application, so there is no such thing as concealing ideas just to make money out of it. And so we have this chance, but in some sense it's like the natural reaction of the human is always try to be competitive. So we have to fight this actively, I think. And one thing is to put a lot of emphasis on the work of our younger researchers. I mean, I think that in math, at least I was lucky enough in my field that I was recognized during my PhD for being an independent researcher, basically. And this gave me infinite confidence, and it made me earn so many years compared to a status where I would have been considered just as, the person who is implementing what my PhD advisor would be doing. So all these years were won, and basically I felt ready just after my PhD to have my own research agenda. I already had it actually, and I think this is something that we should push even more among our younger researchers. So my PhD students for me are my colleagues. They are not my students. Of course, I have a mentoring obligation. I have more experience, so I can help them. But I want them to be independent before anything. So this is something that we should really help the students believing in. And also the collaboration, because again, as I said, we have this chance of being in a less competitive environment, so we can actually benefit much more from each other in a free way. So this is something that I will recommend to everybody.
Excellent, thank you. Okay, what about the audience?
Don't be afraid.
First one is the toughest one.
Yeah,
there you go.
It doesn't have to be on the talk. If you didn't like it,
So, yeah. Hello, Professor. You mentioned the idea of a phase transition between when a material became percolous, porous, or between when suddenly the water like flows through the material.
Yeah.
I just want to trying to interpret this phenomenon in terms of, let's say, making a pour over coffee. Does it mean that when I pour water into a cone-shaped coffee, then at first the water slips through very slowly, and maybe suddenly it makes very large progress into, like, instead of continuously seeping through the depths? Can I interpret it like that?
Yeah, I mean, okay, so you see, I mean, immediately you realize that you should not have explained the, the reason for the model. So of course, I mean, in the case of real percolation of water through a medium, when you make coffee, I mean, the grains are not hexagonal, they are not perfectly preventing water to go through. So the water is going a little bit everywhere in this case. It's just going slowly because there is no much space between the grains. So it's slightly different thing. But if you want to see a phase transition, you could indeed imagine a coffee that would be more and more dense. And then what will happen is that at the beginning it would flow very easily indeed. And then it will start getting harder and harder to flow through, and it will stop flowing through if it's too dense, because there would be no way even in between the grains to go.
So let me conclude. Does it mean that the flow of water in the coffee, there are other factors that matter that influence the speed of water flowing through the
there are many
depth?
other factors, and if you see me making a coffee, you realize that my ability to study percolation gives me no edge on, on making good coffee. So there are many other factors. So it's really, I mean, that's also the beauty of this type of thing, is that you are really caricaturing the physical phenomenon. And what you are doing is actually very far from reality. But again, from this perspective, is that the things that you are going to prove may be applicable to a wider range of models. So that's why, in some sense, we sometimes are complementary to what a physicist or experimental physicist would do.
You?
Maybe over there. Any questions?
Yes.
Thank you for the very insightful and interesting talk. Just wondering how much simulation would help to bring you insight in understanding the underlying math?
So you see, I mean, people invented computers, mathematicians invented physicists. Oh, that's actually a very good line. I like it more than I thought, but maybe not in front of physicists. But so my point is that actually we can base our intuition a lot on the beautiful work that was done by physicists before. So at the level of physicists, they use simulations. Actually, at the time where these things were discovered, they had this poor man Monte Carlo method, so they were actually doing it by hand. But they had simulations, they had experiments, and this helped them actually combine also with mathematical results to come up with a big phenomena or big principle that we now use in our intuition. One of the big ones being universality. Universality came from honest study of different models and noticing that you get the same exponent, so there must be something behind it. And that's where Leo Kadanoff suggested that this is a bigger principle. And it's a principle that exceeds math. I mean, that's one of the reasons why also, in computer science, in physics, in biology, in neuroscience, all these things work, is because our ability as humans to make caricatures of reality combines with the universality principles in nature that make it that, in fact, what we describe from this caricature is not far from the truth.
Thank you, Professor, for your talk. I'm very bad in mathematics, so I want to know that you use some examples like the green coffee and the magnets, I think they have different, like the green coffee, they have different shapes, and the magnets, they affect each other on each polar. So why do you use the hexagon to simulate all this phenomenon? Thank you.
Okay, so first of all, we are all bad in mathematics to a certain level. So the good thing is never to say that you are bad in mathematics in front of somebody that is clearly not as good as you are. This is the place where this becomes bad, because. To go more seriously to the question, I mean, your goal is exactly to draw similarities between different phenomena. I'm not claiming that they are the same phenomena. As you said, for instance, in the random coloring coming from the magnetism, from the magnet, there, for instance, it's pretty clear that if a case, like a square, is red, meaning that the magnet is pointing in this direction, well, intuitively, for the small magnets near to it, what do they want to do? They want to align, right? I mean, this is clearly what magnets do, so that's going to be one of the rules even in your model. So that means that the magnets nearby will have a bigger tendency to be red than blue, the squares behind. So there is there a correlation between the colors of the different things. So it's going to be a percolation model again, but it's not going to be what we call an independent percolation model. It's going to introduce dependency. So there will be similarities, but also things that are not the same. And for the small story, so my cup of tea, if I may say, I mean, the thing that I like really in this area was exactly this dependent model, the one with dependency. When I arrived as a PhD student, we had a fairly amazing understanding of Bernoulli percolation, so independent percolation. But we had a super poor understanding of dependent percolation models. And it's by the way, it's where you see that the sensibility of everybody is important in science, is that my PhD advisor that got this very impressive formula was only interested almost by independent percolation. And when I arrived, the fact that we couldn't understand even the simplest things on the dependent percolation was something that was bugging me completely. Like I couldn't, this was something that I really wanted to understand. So I started trying to answer very simple question from the point of view of my advisor, extremely elementary question for these more general models. What happened is that, in fact, by building this theory of dependent percolation models, I got access to all these applications, in particular to ferromagnetism. So you want to be using the similarities between the phenomena, not forcing them to be exactly the same. You want to have this freedom of applying it to models that are similar but not the same.
Massimo.
Thank you for the nice talk. So you mentioned a couple of times why your PhD advisor got the Fields Medal, but can you give a little bit more details of why you got the Fields Medal? So what was your contribution? Was not totally clear to me.
But that's a very good question. I'm not sure.
Well, no, that's what he told us last year too.
Yeah. No, but I hope that the people in the jury know why. But, no, but so one of the funny things I told that earlier, that the citation is almost entirely based on the application of my work to magnetism, I mean, to the Ising model, which is a math caricature for this. Why, I mean, I was extremely surprised by this, because for me, it's really, I felt it was a corollary of what could deserve maybe a recognition, which was building this theory of dependent percolation models. But it's a very, I mean, I cannot quote a formula. I'm a very different kind of mathematician from that point of view. It's really an accumulation of knowledge of different results that built a global theory of dependent percolation models. That's what I was awarded the Fields Medal for. You see, I mean, I don't know how many people did probability as an undergrad course, or for the lucky people that did a job out of it. I mean, we all know, right, there is one property when you do probability, which is very practical. It's independence. right? I mean, if you don't have independence, you start panicking, you check that the person didn't forget in front of the dependent thing, and like, please, you know. And so that was a little bit the same story for percolation. For independent percolation, obviously, you use independence all the time. If I tell you what happened in this area of the space, it gives me zero information of what happens here, so I can try to play with that tool. What happens when you get a dependent percolation model? It's a little bit more subtle in some sense. And what is funny is that the models that you want to apply, like the models that you get when you try to look at physical systems, of course they have naturally these dependencies that comes just from the forces that are binding the physical system itself. So for magnets, there is a dependency. So you have to, a little bit like you would have to do probability without independence, here you have to do percolation without independence, and that's not easy, but that's very interesting.
Very good. Unfortunately, we have to stop because this is already time for the next speaker. So thanks, Hugo, a lot.
Thank you very much.